let's talk about section 15, theorem 1. But before we do that, let's discuss decimals and very specifically terminating decimals. So I'm going to give you two different examples. So let's say we have 0.2. First example, so 0.2, we know it terminates. And we also know that if we multiply 0.2 by 10, it gives us 2. So we can rewrite 0.2 as a fraction divisible by 10. So this can be rewritten as 2 over the 10. I can rewrite 2 over 10 as 2 to the first power and 10 to the first power. We also know that 10 factors in, the factors of 10 are 5 and 2. So we can also say this is 2 to the first. 5 times 2 to the first, which is also 2 to the first. 5 to the first times 2 to the first. 2 to the first power over 2 to the first power simplifies to 1. So this can then finally be rewritten as 1 over 5 to the first power. Let's think of another example. So let's say 0.025. If we multiply this by 1,000, this becomes 25. So then we can rewrite that decimal expansion as 25 over 1,000. And 25 over 1,000 can be rewritten as 5 squared. 1,000 can be written as 10 to the third power, and that can also then be rewritten as 5 times 2 to the third power, which is also equivalent. If we distribute the 3, then that is 5/3 times 2/3. So here, 5 squared here in the numerator simplifies, gives us 1 over 5 to the first times 2/3. 3 minus 2 giving us 1. So just to note here that 5 to the third minus 5 squared gives us 5 to the first power, and that is how we got that. So this is the premise, the setup of Theorem 1's proof. So then first, the proof relies on the fact that each one of these decimals is divisible by 10 to a certain power. Okay, so let's say that. So let's say let m be the maximum, or whatever power 10 it is. So be the maximum of A and B. Then let's say 10 to whatever power times 1 over, we'll say 2 times to the power of A and 5 times to the power of b. This then says, if we put this over 1, we know that if we multiply whatever is in the denominator, this is also can be rewritten as 2 to the power of m times 5 to the power of m per our example. So then this is 2 times a, 5 times b. And so when we have the same 2 on the numerator and denominator, we can just subtract its exponent. So then this gives us 2m minus a times 5m minus b. And we'll call this an integer. We'll call this to be, this is an integer per our example. We'll call it n. So we know for sure in our examples up here, n is less than 10m. So we know n has to be less than or equal to 10m. So then thus, we can say, thus 2a 5b must equal n over 10 to the m decimal expansion consists of digits n possibly being preceded by some 0. This proof then gives us the theorem of section 1, theorem 1 of section 15, which basically says if A and B are any non-negative integers, then the decimal expansion of 1 over 2a 5b must then terminate.